Okay, we are continuing with the Further Maths chapter summaries, and this one is Methods in Calculus, which is Core Pure Year 2, Chapter 3. And like I always say in these videos, it is not possible for these chapter summaries to cover all of the possible ways that you can be assessed on these topics. So please make sure you have done thorough revision. This is really just as a quick kind of recap of what came up in this chapter. So the first thing that we're going to deal with is improper integrals, and I've only picked one example for improper integrals, but there are plenty of ways that they can be asked about, so really do make sure that you dedicate enough time to each of these kinds of examples. So an improper integral is one where either the one or both of the limits is either positive or negative infinity. So you can see in this one here we've got a limit that's infinity, so it's an improper integral. It could be where the function is undefined for either one of the limits, either the bottom limit or the top limit. And when I say undefined, it could be something where maybe the denominator becomes 0. Obviously we can't divide by 0. Or it could be where the function is undefined for a value inside the interval. So whether it was, I don't know, 2 and 5 on the top, but it's undefined at 3, we still need to treat that using improper integrals. And in the sake of, for the purpose of not making this video too long, I've picked one of these types. Do make sure that you have a quick look through the other types that there are. What you do for this is you replace the limit, as in the top or bottom part of the integration sign, with t, and then you apply limits, meaning kind of like mathematical limits of what we have here. Now, I wanted to very quickly talk to you about some of this idea of when we're talking about limits with things like this, and I thought I would do it with a particular example, this time with just the reciprocal graph, or y equals 1 over x, because in the most recent exam, in the edXL 2025 exam, there was a question where we had to understand the difference of some of these kind of symbols that we've got down here, and I thought it kind of is briefly touched on in the playlist, but I'll be able to kind of go into a bit more detail here. So when we talk about taking limits, we're now thinking about this graph. What happens to y as x goes towards infinity? So we're saying as x gets really, really big, y goes towards 0. But I think we can actually be even more specific to this. And we can say it goes towards 0, but it goes to 0 from the positive side. So I could say that it goes to 0 from above. That little plus sign means it's approaching it from the positive side. As x goes to negative infinity over here, y is indeed going towards 0, but it's approaching 0 from below the axis. So we would say that it's 0 below. And then to talk about the differences of these parts, when x approaches 0, you can actually see that it's either going to, for y, going to be positive infinity or negative infinity when x is at 0. So it depends if we're approaching it from above, 0 plus, or from below, 0 minus. So if we were approaching x from going towards 0 from above, y goes very, very big. So y would go towards positive infinity. But if we were approaching 0 for x from below, from this side, y is very, very negative. So we have negative infinity. And if you're interested in looking at the question that uses this, I think it's towards the end of the first Core Pure paper from the edXL 2025 papers. And just in terms of how you should do your writing for this kind of stuff, it is importantly to consistently write the limit part at the beginning throughout your working out, because that is part of the way that we're communicating these things as sort of like effectively as possible. So it says here, show that the following integral converges, sometimes they will diverge, and find its value, giving your answer in the form k ln2, where k is a constant to be determined. So it's definitely an improper integral because of the fact that we have this infinity in the top limit that we've got here. So we're going to rewrite this, and instead of having infinity, like we said, we will replace it with t, like this, but we're going to have to write at the beginning the limit as t approaches infinity of 1 over x, x plus 4 with respect to x. Now I'm going to just work on doing the actual integration part of this. To do that integration, I am going to need to use partial fractions on this. So I'm going to do some partial fractions, and my partial fractions that I've got here is going to be on this 1 over x, x plus 4. So that will be my a over x and my b over x plus 4. So we have 1 is a with the x plus 4 plus b with the x. So when x is equal to 0, we get 1 is 4a, and so a is a quarter. And when x is minus 4, we get 1 is minus 4b, so b is equal to minus a quarter. So that means we can now actually rewrite this question, and we can do it using, we can do it as a partial fractions instead. So every time we're going to say this is the limit as t approaches infinity between 4 and t, we then have the a over x plus the b, which is negative a quarter, so it's going to be negative a quarter over x plus 4. Now, if you wanted to, you could rewrite this one so that it's 1 over 4x, and this one we could write as 1 over 4 brackets x plus 4. But if you've watched lots of my videos before, you'll know I actually find it easier having it in this form that we've got. I find it easier to do the integration part. So we'll actually now go straight in with doing the integration because those are in an integratable form. So this one is just going to be a quarter ln x, and this one is going to be minus a quarter ln of x plus 4. So leaving those quarters at the top kind of made that a bit easier. And we will put our 4 and t in for this bit. So there's an option here. We can either go straight in with doing the substitution with the t and the 4, or we can combine these things into one single logarithm. I'm going to show you they are going to be better to be combined. I'm going to show you why they're better to be combined by not combining them, and then hopefully we'll figure out why that's better. So still writing that limit part, I'm going to substitute in t. So there's going to be my quarter ln t minus a quarter ln of t plus 4. And then from that, we'll be subtracting when we substitute in 4. That is going to be a quarter ln 4 minus a quarter ln 8. Okay? So let's now see what happens as we do these parts here. Have I got those values incorrect? Yeah, I did have a 4 at the bottom. Now, the thing is, when you start trying to take limits with t going towards infinity, this thing, ln of infinity, also goes towards infinity, and this also would go towards infinity. So we actually can't evaluate that limit. So what we're going to do instead is we are going to combine them and then think about what happens to those parts. So this is going to be a quarter ln of, they've both got a quarter there, it would be t over t plus 4. We're then going to be subtracting a quarter ln 4, and then there'll be a plus quarter ln of 8 for that bit. Okay, so now we can start to think to ourselves, what happens to this thing when t goes towards infinity? So there's plenty of different ways of thinking about this, but I'm going to just kind of explore it over here and say, as t goes towards infinity, oh gosh, terrible infinity sign there, we have t over t plus 4. One way of thinking about it is you're going to have infinity over infinity plus 4. In other words, infinity over infinity, so that must be going towards 1. But I'm going to show you a better way that we might like to think about this. If I divide this top part by t, and I divide everything in the bottom part by t, I would get 1 over 1 plus 4 over t. Now 4 over t, as t goes towards infinity, when you do 4 divided by a huge number, it goes towards 0. Hence, we can say that 1 over 1 plus 4 over t just goes to 1 over 1. In other words, it goes towards 1. Which means that we can now say this is equal to, we're actually going to take the limits, this goes to a quarter ln 1 minus a quarter ln 4 plus a quarter ln 8 for this part, okay? This part now goes towards 0. We just need to kind of tidy up this last stage that we've got here. So for this last stage, I'll do the positive one first. We have my a quarter ln 8 minus a quarter ln 4. Well, they've both got a quarter with them, so I can simplify it as an 8 divided by 4. And 8 divided by 4 is 2. So we have a quarter ln 2, as we were expecting to see in the question here. So k in this case is equal to a quarter. So this technique, if you want to kind of ever figure these things out, you can sort of do that division through by things. For example, if we had something that was a little bit different, 2t squared plus t plus 1 over t squared plus 3. This time, instead of dividing by t, we could divide by t squared and divide by t squared, so that we get 2 plus 1 over t plus 1 over t squared, and then you just get 1 plus 3 over t squared. Very quickly we can see that as t goes towards infinity, this, and this are all going to go towards 0, so the overall thing is just going to go towards 2 divided by 1, it just goes towards 2. So this technique of division through stuff can be helpful. If you do further pure, you'll probably be quite familiar with that stuff. So I've tried to kind of squeeze as much as I could about improper integrals into just one example with this, but do check out some of these other ones about how we might split some of these things up as well. So the next thing that gets covered in this chapter is inverse trigonometric functions, arcsine, arccos, and arctan x. And these things are given to us in the formula book about how you differentiate these things like this. So I kind of don't memorize them. I have a rough idea of what they are, but I would then kind of refer to this from the formula booklet to do this. So to differentiate these inverse trigonometric functions, I have my arcsine x squared. Well, it's already kind of looking like this. It's just instead of an x, we have an x squared. So it's going to be this same pattern, but where there's x, there's going to be an x squared. And of course, we have to apply the chain rule to this. So to differentiate, I will have that dy by dx is going to be equal to arcsine x will go to 1 over the square root of 1 minus x squared, all squared, multiplied by the derivative of this inside function, which is 2x. So it just differentiates to 2x over the square root of 1 minus x to the power of 4. The second one, we have a strange looking function. We have arctan of sine x. So again, it's going to be a chain rule. It's going to go to this form, but instead of an x, there will be a sine x. And we have to multiply by the derivative of sine x as well. So that's 1 over 1 plus sine squared x, multiplied by, let me just make that sine squared look a little bit clearer, multiplied by the derivative of that sine x, which is cos x. So it is just cos x over 1 plus sine squared x. And when I wrote this, I was like, that looks like it should simplify. It doesn't simplify particularly neatly. If it was obviously a 1 minus sine squared, it would be a completely different thing. And then I wanted to show you this one, got it written in a slightly different form, inverse tan x. Obviously, that's the same as arc tan x as well. So we are going to still apply that same pattern that we've got here. So our dy by dx is going to be 1 over 1 plus that inside part all squared. So that's going to be my x over 1 minus x squared. And then it's going to get multiplied by the derivative of this inside part. So that inside part that we've got there, I'm actually going to do that differentiation of it somewhere else, okay? I'm going to use the quotient rule for this, and I'm going to say that my u is equal to x, and my v is 1 minus x. X differentiates to 1, and 1 minus x differentiates to minus 1. So when I do the quotient rule, I will have my v u dash, this one, minus this times this one, divided by v squared. So I have the 1 minus x multiplied by 1, minus these two things multiplied. So that's minus x, minus x, all divided by v squared, which is 1 minus x squared. So it differentiates to a 1 minus x plus x. In other words, it differentiates to a 1 over 1 minus x squared. So it gets multiplied by 1 over 1 minus x squared. Okay, we'll just do a bit of tidying up with this. It doesn't say we have to do the tidying up, but that's what I want really to happen here. So this is a 1 plus the numerator squared and then the denominator squared, and it's getting multiplied by 1 over 1 minus x squared. So this 1 minus x squared, when we multiply it with this, it's going to multiply by the 1, and it's going to multiply by this part. Those parts are going to cancel out, and we're going to get, hopefully, a relatively neat-looking thing. So the numerator is 1. The 1 times the 1 minus x squared is 1 minus x squared. And that second part, we said that the denominator will cancel with the 1 minus x squared. We could leave it in this form if we want to. I'm probably going to do a little bit of expanding so that I would have a 1, a minus 2x, and then a plus x squared and a plus x squared. Let's just save a bit of time, and let's just write that as our plus 2x squared in the denominator. You know what? If you left it at this stage, I think this is also a very good way of it being written. Okay, we're now going to have a look at doing integration with inverse trigonometric functions. So again, the formula booklet, the formulae are very helpful here. If you are asked to choose a suitable substitution, the formulae are a clue for which to use. I'll discuss that down here in just a second. And of course, if you're going to just do it without the formulae, without the substitution, please be sure to manipulate the expression to reflect the formula exactly. And what I mean by that is making sure that we have the x squared by itself for this part, okay? So we will be tackling some of these later on in the hyperbolic playlist, because I've only included these two for now, but when the hyperbolics get introduced in chapter 6, I will be returning to some of these things. If you are looking for what the substitution is for something that looks like this, We can clearly see it's going towards arc sine. That means it's going to be a substitution of this form that we've got here. And you'll see when we do the substitution why that creates something really neat in the denominator. If it's arctan here, we'll be using tan u, a tan u, and a sine u. And it's the same pattern when we come across the ones with sine x, cos x, all sorts of stuff like that, depending on what's going on in the integration part that we've got there. So for the first one, we are actually going to prove that this formula is true, that this thing integrates to this thing plus c. And the clue is the substitution. It'll always be a version of this thing. It'll be the a sine u in this case. So we are going to start off with our substitution. We are going to say, let x be equal to a sine u. So I'm going to build up this a squared minus x squared, okay? The a squared minus x squared will be a squared minus x squared. That's a squared sine squared u. I can factorize out the a squared, so I get a squared 1 minus sine squared u. 1 minus sine squared is cos squared. So we get a squared cos squared u. So a squared minus x squared is this. So the square root of a squared minus x squared is just going to be a cos u. That was the whole point of picking this as our substitution, that this denominator has now simplified to something really, really nice like this. So we also need to figure out now what the dx part is for this. Okay, we're going to have a look at doing this part with dx. So if x is equal to a sine u, I'll differentiate. So I get that dx du is equal to a cos u. Sine differentiates to cos, so dx is a cos u du. Okay, I think we're actually probably ready to go and actually do some substitution. So I'm doing the integral of 1 over a squared minus x squared dx. That is the same as integrating 1 over a squared minus x squared square rooted, we said is a cos u, and dx in this case is a cos u du. So that's a cos u du. So these a cos u's are cancelling. So we're literally just integrating 1 with respect to u, which is just u plus c. So all we need to do now is find out what u is equal to. And in fact, I can probably do that over here. If I give myself a little bit of extra space, I can say what u is equal to. So maybe I'll do that in this red colour that we've got. So if I do x divided by a, that is equal to sine u. So arc sine of x over a is equal to u. So I can actually go straight into this part over here. I'll do it in the red colour, and I'll say that u is equal to arc sine x over a plus c. Now they had the brackets around it. I don't know if it's necessary for this, so we can leave it in that form that we've got there, and we have shown that it is equal to this thing that you've got. So the substitutions will mostly take that kind of similar sort of pattern of this denominator simplifying to something really neat. This one that we get down here, you end up with something like the 1 plus tan squared simplifying to sec squared kind of thing. So you do get lots of things cancelling out with that stuff, and generally just leave it in the denominator because it's usually going to cancel with the derivative of this part that we've got there. Okay, this one says evaluate this. In other words, let's just do this integration. So the thing we are going to say which one it looks like out of the choice between this one and this one doesn't have the square root sign. So it is going to be one of these with the arctan kind of thing. It's this form that we've got here. Now the difference is this one is an x squared. This one has a 3x squared. So I think I'm going to need to do a little bit of division by 3 in the denominator so that I have 4 over. If I take 3 out, I would have 16 over 3 plus x squared dx. And I'm going to make my life even easier. I'm going to take this 4 over 3. I'm going to pull it right to the front as a factor so that I have 4 over 3, and then I'm left with 1 over 16 over 3 x squared dx. And then looking at the formula, I just need to really extract what a squared is equal to. So in this case, a squared is 16 over 3, which means that a is 4 over root 3. Now, generally, I recommend just kind of leaving it in this sort of form rather than rationalising it, because you'll see there's a 1 over a, and it's then much easier to take the reciprocal, and then it's already in its rationalised form that we've got there, which is why I didn't put this sort of square rooted on the calculator. I just find it a little bit easier to do it like that. So we get left with the 4 over 3. It's then going to get multiplied by the 1 over a, meaning the reciprocal of this, which is root 3 over 4. And then we get arctan of x over a. So this is going to be x over 4 over root 3. That's, again, over a is the reciprocal of that. So it's still going to be the plus c. The 4's cancel at the beginning. So we have our root 3 over 3, arctan of root 3 x over 4 plus c. That x could be in the numerator, or it could be to the side like that as well. We just simplified this fraction into this one that we have got here. Okay, next up is integration with partial fractions, and this is going to start using some of these things from the formula booklet as well. So I've included them here once again, plus this additional one that we've got here. So something we need to know for sort of partial fractions from further maths. When you do partial fractions, the numerator must take the general form of a polynomial 1 degree lower than that of the denominator. So for example, if the denominator is an x squared plus 3, which obviously can't be factorized anymore, you always want to factorize the denominator as much as possible, the numerator won't just be a b or an a by itself. It won't just be a constant. It has to be a general form of a linear that we've got here. If you were to have something like this, which would be very unlikely, something like x cubed plus 2 on the denominator, the top would need to be an ax squared plus bx plus c. It needs to be a polynomial that is 1 degree lower than the denominator. Okay, I would not expect to see something with a cubic, but just in case it is there, you are aware of that as well. And you'll tend to find that it's when you do partial fractions, it's a good idea to use comparing coefficients rather than substitution, because substitution for something like this, you would have to use like an imaginary number. So I prefer doing comparing coefficients. Now there is one more thing that is in the formula booklet. It's for things that look like this kind of form. There is a very quick way of integrating things that look like this. If you wanted to prove this final result, all you need to do is to factorize the denominator into a difference of 2 squares, double brackets, do partial fractions, and then you come up with some stuff to do with logarithms, and it recombines to look like this. If you didn't use this from the formula booklet, and you have a good solid knowledge of partial fractions, you will find yourself getting to the same answer as well. It just can be a bit of a time saver with some of this stuff. So this one wants us to integrate this expression that we've got here. Now, we should notice this is a cubic and this is a quartic. If the numerator was also a quartic, we would need to use those techniques from year 1, where we would need to do algebraic division to find out what would be the constant term from the division. But in this case, because it's a cubic and a quartic, we can just go straight into trying to do what the things are with partial fractions. So let's actually deal with this, right? We have our 2x cubed plus 2x squared plus 8x minus 1. I think we're obviously not going to just do a very general one for the bottom. We have to do some factorizing, right, to even do partial fractions with this. So if I was going to factorize this bottom part, it looks like a pseudo-quadratic, where it's like a quadratic, but in terms of x squared. So I think there's going to be an x squared bracket and an x squared bracket. I need to think of two things that multiply to 4 and add to 5. It's going to be a plus 1, and it is going to be a plus 4 for this, meaning that we have an a over x squared plus 1. Oh, hang on, I've not even taken my own advice, have I? If it's a quadratic on the bottom, that means it's going to have to be a linear on the top. And again, we've got another quadratic over here, our x squared plus 4. This is going to have to be a cx plus d, like this. So our 2x cubed plus 2x squared plus 8x minus 1 is going to be our ax plus b multiplied by our x squared plus 4. And it's going to be our cx plus d multiplied by x squared plus 1. And this is where I prefer doing comparing coefficients, okay? If we compare the coefficients, we should come up with a set of different equations, and we should be able to solve them. So I'm going to compare to start with the x cubed terms. On the left-hand side, there is a 2x cubed. To get an x cubed here, the only way I can get it is this times this. So there's going to be an a and a c. That's the only way we can get it. If I compare the x squared terms, there's a 2 on the left-hand side. I can get an x squared like this. That's the only way I can get it from here, which is a b and a d. So it's b plus d. If I compare the x terms, there is 8 on the left-hand side. To get an x term here, there's going to be 4a, no other way of getting it, plus c. So that is 4a plus c. And then if I compare the constant terms, so con is for constant there, that is minus 1. The only way we get a constant from here is the b times 4, so that's 4b. And then from this last one, we get the d times by 1, which is just d like this. So you can either just put these onto your calculator, however you want to solve these things, but they actually look pretty easy to do. So if I called this one equation 1, equation 2, equation 3, and equation 4, if I do equation 3 minus equation 1, so I'm doing this one, take away this one, the left-hand side would be 6, and we get just the 3a's, the c's cancel, which means a is equal to 2. And if a is equal to 2, that means that c is equal to 0. So a is equal to 2 and c is equal to 0. And then if I do equation 4 minus equation 2, we get some really nice ones. Again, they might not be this nice, so you'd have to use lots of techniques, or you could get them onto your simultaneous equation solver. So I'm doing this one minus this one. Minus 1 minus 2 is minus 3. 4b minus b is 3b, and the d's cancel out. So this means that b is equal to minus 1. And so if b is equal to minus 1, that means that d is equal to 3. Yeah, minus 1 goes to the other side and becomes 3. So that means that d is equal to 3. So now that I've got it written like this, I can actually go ahead and do the integration. So I'm going to just sort of pretend. Let's just box that off. I'm going to pretend that this expression is written like right next to the equal sign, okay? So I'm actually integrating it with these new coefficients. So a is 2 and b is minus 1. So this is a 2x minus 1 over x squared plus 1. So this is a 2x minus 1 over x squared plus 1. C is 0 and d is 3. So it's plus 3 over x squared plus 4. With respect to x. Okay, so we've done the partial fractions. We can now just get on with doing the integration as normal. But I have written this little extra clue down here. Splitting the numerator is useful because looking at these formulae, right, we've got something that looks like this one, but we don't have something with this as the numerator. So I think if we split this into two parts by splitting the numerator up, we should be able to figure out what the integration is going to be. So this is going to be a 2x over x squared plus 1. Minus 1 over x squared plus 1 plus 3 over x squared plus 4, like this, okay? So this is probably the hardest one to spot because it's not from the formula booklet. This is just normal integration, right? The numerator happens to be the derivative of the denominator. So this is actually just going to be the ln of x squared plus 1. Now, obviously, I don't really need the modular signs here because x squared plus 1 is always going to be positive. But if you did put them in, you wouldn't be penalised for that. And then for this next one, it looks like it is of this form that we've got here, doesn't it? Apart from a in this case is going to be equal to 1. So it is going to be minus 1 over 1 arctan of x over 1. Just being really explicit with that. There is a 3 for this part, so I'm going to have the 3 there, and it's going to get multiplied by 1 over a. Well, a squared in this case is 4, which means that a is 2. So it's going to be 1 over 2 arctan x over 2 plus c. All that's left is a bit of tidying up, so that's the ln of x squared plus 1 minus arctan x plus 3 over 2 arctan x over 2 plus c. So didn't actually use that much space in the end. I could have been a bit more generous. I could have used a lot more space here. Make sure that you're aware of what the standard forms should look like for partial fractions. This box up here is going to be particularly useful. And if you want to, you could go and have a go at proving this one as well. Okay, we are going to finish up with the mean value of a function. Even though this is taught right at the beginning, the reason I've put this at the end is so that we get a bit more practice with doing some of the integration techniques that is from this chapter. So I've deliberately put this one as the last part that we've got here. I'm not going to go too much into the theory of this, just going to talk through the language of this. Kind of the mean value of a function is exactly what you'd expect it to be. Like over a particular interval, you've got the area of that function, and we're just saying, well, what's the average value of that function in that interval? And I do go through this in a bit more detail in the playlist where I teach this. So just like in statistics, we use this bar to show the average value of f of x, the mean value of f of x over the interval between a and b. Well, you find the area of the function and you just divide it by the gap of that function. You just, the gap of that limit, the gap of the interval that you've got there. Something that does kind of get touched on, again, this just makes sense with how averages work that we've got here. If I wanted to find the average of a function that has been scaled by p and we've added q onto it, well, you just take the average of the previous function, you scale it by p, and you add q onto it. Luckily, it just behaves exactly how we would expect this thing. So the theory of mean value of a function is very straightforward. What they love to do in the exams is to do it for basically just to test all the integration that is from this chapter. So we have that f of x is equal to x plus 3 over the square root of 9 minus x squared. And we're going to show that the mean value of f of x over the interval 0, 3 over 2 is this thing. Okay, well, mean value of a function means we're going to have to do the mean value of f of x. We're going to have to do some integration. So it's going to be 1 over, once between 0 and 3 over 2. So it's between 0 and 3 over 2. Well, the denominator will be 1 over 3 over 2 minus 0, or just 1 over 3 over 2 if you'd prefer it like that. And the thing we're integrating is my x plus 3 over the square root of 9 minus x squared. 9 minus x squared dx. So we have 1 over 3 over 2. That's 1 over 3 over 2 is 2 over 3. We're integrating between 0 and 3 over 2. We're going to use this same thing. I've said it's going to be coming up quite a lot in this. We're going to split the numerator because as it currently stands, this does not look like either of these things that we've got here, any of these things. So we need to make sure we split it up into these different pieces. So when I split the numerator, I'm going to have an x over the square root of 9 minus x squared plus 3 over the square root of 9 minus x squared dx. This one looks just like the formula for sine, okay? It looks almost just like it, apart from it's got a 3 in the numerator, so it looks just like this one. The other one we're going to need to be a little bit more thoughtful for, and I think this is where it can be a good idea to write it in index form instead. So if I write it like this, x 9 minus x squared to the minus a half, and then this one I'm just going to keep the same because it's already in a form that we like the look of. I'm hoping you might be able to tell me what this is going to be. How are you going to tell me? It's a video. But I'm hoping you might be able to think to yourself what this is going to be for integration. It is an example of the reverse chain rule. So it is going to be a 9 minus x squared to the power of a half. Now, the reason it's reverse chain rule is the derivative of this thing is minus 2x, and there's an x here, so there's a relationship between it. We're just going to say, what does it need to be? Let's just quickly run through this in our head. If it went to this part where I've integrated the power by, I've increased the power by 1, let's just differentiate it and see what we'd get. We'd pull the power down, and then we would reduce the power by 1, but we would also multiply by minus 2x. So there'd be a half and a minus 2x, which would be a minus x, but I want there to be an x, so I need to counter it by putting a minus in there. If I went a bit too fast for you there, I hope it wasn't too fast, but at this stage, it's just a quick bit of revision video here, so you might need to just go back and do a little bit of extra practice on some of that integration. And then for this part, the 3 is going to stay there, and we've got basically the 1 over 9 minus x squared. So the a squared is 9, and so the a is 3. So it's just going to go to arc sine of x over 3. Arc sine of x over 3. 3 arc sine x over 3. Okay, don't know why I've done those brackets. I'm going to want to put those square brackets in, aren't I? Because we're actually doing integration with some limits here. So we're going from 0 to 3 over 2. So let's sub in 3 over 2 for this. And I probably will be a bit lazy and use the calculator. So it's going to be 3 over 2. So I'll do 9 minus 3 over 2 squared, square rooted, and then negating the answer. So that is going to be minus 3 root 3 over 2 plus 3 arc sine of 3 over 2 divided by 3, which is a half. And then when I subtract 0 from this, when I subtract them with 0 substituted in, there will be a minus 9 to the half. That's going to be a minus 3. And then we also have a plus 3 arc sine of 0. So this is 2 over 3 minus 3 root 3 over 2. Arc sine a half is 30 degrees, but we're in calculus here, so it's going to be pi over 6, and that's going to get multiplied by 3. So that is pi over 2. And then we have a minus 3, which is a plus 3, and arc sine 0 is 0, so we can just ignore that part All that's left is to multiply by the 2 over 3 and have it in the order that they wanted, which is the 2, the minus root 3. So the 2/3 times 3, yep, that's the 2 that we were expecting. If I now do this times by this, well, the 2 and the 3 over 2 are going to cancel, so we do just get a minus root 3. And then 2/3 multiplied by that half is just a pi over 3, which was the last part that we were expecting for this. So really they're using the mean value of a function as just an opportunity to say like, hey, do some integration for us. It then says, hence calculate the mean value of this function. So all I really want to do is decide what this function is, how it looks different to this function. So it looks like 2x plus 6 over the square root of 9 minus x squared minus 4. To me, I can see what this is straight away. It looks like the numerator has gone from x plus 3 to 2x plus 6. So it looks like this is just doubled. And then afterwards, we've subtracted 4. So it looks like 2f of x subtract 4. Hence, the mean value is going to be the mean value of the previous one times 2 minus 4. So that is going to be the mean value of the previous one times 2 minus 4. So we can finish this off. That's the 2 times 2, which is 4, minus 2 root 3, plus 2 over 3 pi, minus 4. The 4 and the minus 4 cancel. I'll start with the positive one. So we get 2/3 pi minus 2 root 3. This is a big chapter. Lots of integration going on in this one, okay? Lots and lots and lots of integration. And it does come up again when we look at the hyperbolic stuff, hyperbolic integration in chapter 6. Things I want you to do after this video is to go and try some other kinds of questions with partial fractions. I didn't want to do like hundreds of questions. I wanted to just kind of use this as a quick bit of a refresher. And other thing I want you to do after this video is to go and have a look at some other improper integrals, particularly one where it's undefined inside the interval, because that's where you'll need to use two different limits to kind of do that part. Again, that's covered in the playlist of videos. And I think that should have you set up pretty much for doing some good revision on this chapter. I hope you're finding these videos useful. If you are, keep on watching them and get yourselves prepared, ready for these exams. Good luck, guys, and I'll see you in another video sometime soon.